The key things about rolling without slipping is that in order for this to happen, the point of contact, so the place where, whatever's rolling, say it's a wheel and the ground, wherever those two come in contact, that point is still. They're not sliding past each other, because that's what without slipping means. And that, of course, then means that the velocity there, sort of like the total velocity, so taking into account all the different ways something that's rolling is moving, at that point, it's zero. And so looking at this object, so a little roll of tape that I've got, if it's rolling around the ground, which I'm doing with a pen, you can maybe sort of see that as I roll, if it's not slipping, the piece of tape, which is touching the little marker here, they're not moving relative to each other. So that's what I mean when I say the point of contact is still, that the velocity there is zero. And the whole reason that something can roll without slipping is because of friction. Friction between whatever's rolling and the ground, that's what causes the rolling. And you can sort of, this has to be true because, if you've ever tried to drive on ice or drive in something really muddy, you don't get the nice situation where you turn your tires and then the car moves. You get the situation where you turn the tires and they just spin. They don't help the car move at all. There you have a lot of slipping because you don't have much friction. So we need the friction to cause the rolling. And if it's rolling without slipping, we know that that friction is static friction. So if we do rolling without slipping, then this is static friction. And that's because, here, the point of contact is still, and so they're not moving relative to each other, so that makes it static friction. And one of the nice things that it turns out we can do in this situation is we can split the motion into two basic things of what's going on. So we're going to split the motion into just rotation. So just thinking about how it's rotating, not considering how it's moving from place to place, and just translation. So here, we're going to think just about how it's moving from place to place. We're going to ignore the fact that it's rotating. And when we add those together, then we'll get the rolling. So first, we got just rotation. So here we've got our wheel. It's not very round, sorry about that, but it is rotating, say this way, and then with the right hand rule, that lets us know that the angular velocity is into the page like that. And if we're looking at just the rotation, we can look at the tangential velocity. And we know that the tangential velocity is always given by this equation. B tangent equals the radius, or really the distance from the axis of rotation to the point we're interested in, wherever we want to measure the axis of rotation. So it's equal to that distance times the angular velocity. So for example, this point right here, what's the tangential velocity there? Well, we need this distance r, and the tangential velocity is going to be pointed down like this because of how it's moving. So there is our first tangent. It'll be r1 times omega. And then maybe we'll do this point right here. That has a little bit longer r. We'll call that r2. And because of how it's rotating, the tangential velocity will be pointed that way. So that'll be tangential velocity 2. It'll be equal to that different radius times the omega. And then up here at the top, well, that'll be the full radius, so I'll call it big R there. And then V tangent at the top, that'll be equal to big R times omega. I guess we could also do V tangent in the center, right there, but that would be 0 because R is 0. There's no distance from the axis of rotation that we're considering in the middle with just the rotation to the point we're interested in. So there's no tangential velocity in the center. And down here at the bottom, well, I guess it's rotating like this, so V tangent would go this way. Oops, I forgot to draw that arrow in. So V tangent at the bottom is equal to, again, the full radius, because that's the distance from this axis of rotation, when we're looking at just the rotation, to where we're interested in, times omega. So we have all of these different tangential velocities when we look at just the rotation. Now let's look at just the translation. Okay, so here we're not looking at how it's rotating. We're just looking at the fact that we have this wheel and that it's moving. So here we're looking at the center of mass velocity. So that is the center of mass velocity. It's just moving this direction, and every single point is going to be moving, translating with this speed in that direction. So like this point, for example. It has a center of mass the exact same as this point does, and at the top we have a center of mass velocity that's exactly the same as the one in the middle, and at the bottom we have a center of mass velocity that's the same as all the other ones. So an important point here for the translation, the center of mass velocity, which I'd been abbreviating as COM up here on the drawing, that is the same for all points. Everything's got the same center of mass velocity because they're all moving from point to point in exactly the same direction at exactly the same speed. All right, so we've got just the rotation, looking at the tangential velocities, and just the translation. If we combine those, we will get the rolling motion. So here we're looking now at the total velocity, which is going to be the translational velocity from over here plus the center of mass velocity from just the translation. Oh, sorry, that should be tangential velocity. I misspoke. So the total velocity is going to be the tangential velocity over here plus the center of mass velocity from here. And you can see that if we did this for just random points, it can get pretty complicated. So for example, if we looked at this point, here we've got a tangential velocity that's sort of pointing down. Here we've got a center of mass velocity that's pointing off. So the total velocity for that point is going to be, you know, kind of the combination of these two. But let's look at just 3 points. Let's look at the middle point. So here we've got a center of mass velocity, but no tangential velocity. So in the middle, we're going to have the total velocity is just equal to the center of mass velocity, because there is no tangential velocity. So let's go ahead and draw that in. It'll just be the center of mass velocity. At the top, we'll have the total velocity is equal to the center of mass velocity plus the tangential velocity. And that is going to be equal to, well, we'll see right here, that is equal to R times omega, big R, because it's the full radius of the whole thing. So that is going to be a longer arrow. And then down here at the bottom, we have the total velocity is equal to the center of mass plus the tangential. and running out of room there. But we also know the point of contact is still. So the velocity there is 0. So at the bottom, we know that v total equals the center of mass velocity plus the tangential velocity. And the tangential velocity is r plus omega, but it's pointed off this direction. So I guess we sort of implied, let's put vector arrows here. If we make the center of mass velocity direction positive, then this one's negative. And we also know, because it's rolling without slipping, that the total velocity here is 0. And that tells us that when it's rolling without slipping, the center of mass velocity is equal to the outside radius, big R, times the angular velocity. And if we do a derivative of that, well, then we can get, the radius isn't going to change, but the angular velocity will become the angular acceleration, and the center of mass velocity will become the center of mass acceleration. So that'd be true. And if we take an integral, then, well, nothing's going to happen to the total radius, but the angular velocity will become just the angular distance, and the center of mass velocity will become the center of mass distance. And I'm not going to use the normal one that we use there, r, for disposition, but remember, this doesn't have to be x, it's just the distance traveled. So it could be y or z or combo, depending on how you set things up. But these things are true if you've got rolling without slipping, and only if you've got rolling without slipping.